we've distinguished between collisions up until this point in a number of different ways. We've said we have one-dimensional collisions and two-dimensional collisions. We said we have T-bone collisions and glancing collisions. We have collisions in which both objects stick together and both objects bounce apart. There's lots of different ways of categorizing collisions. The way we learned to categorize them yesterday was based on none of those things. It was based on kinetic energy of the collision. We said yesterday that we have two types of collisions: an elastic collision, in which of course momentum is conserved, because momentum is always conserved, but kinetic energy is also conserved. You have the same amount of kinetic energy after the collision as you have before the collision. Now, the other kind of collision, if we're going to distinguish it based on kinetic energy, is called an inelastic collision. This is a collision in which momentum is still conserved, because as long as we have an isolated system where we have no external forces, then momentum has to be conserved. But in an inelastic collision, kinetic energy is not conserved. Kinetic energy is lost. It disappears. That doesn't mean energy is destroyed. The law of conservation of energy still holds. The energy just goes off in some other form. As opposed to being kinetic energy, it would likely go off in the form of heat, mainly heat, maybe a little bit of sound, maybe a little bit of light, depending upon the context, but mostly it would go off in the form of heat. So elastic, momentum, and kinetic energy is conserved. In inelastic, we have just momentum conserved, kinetic energy is lost. Now, we talked about a number of different examples of kinetic energy, collisions yesterday, elastic and inelastic. We said two billiard balls colliding was pretty close to elastic. Two curling rocks colliding was pretty close to elastic. A basketball bouncing off the floor was inelastic. Two cars colliding was inelastic. The difference between those collisions was the hardness of the objects. When we have two objects colliding that won't compress, that won't deform, that won't change shape, that won't squish, then they're going to be pretty close to an elastic collision. Here's the reason why. You guys learned in Science 10 about the second law of thermodynamics. Anytime you have an energy conversion, you always lose a little bit, right? When you lose a little bit of energy in a conversion, it means you can't have as much afterwards as you had when you started. When two objects hit each other in squish or compress, there's a conversion taking place from kinetic to elastic potential energy. If that conversion takes place, you've lost some energy in the form of heat. So you can't possibly, at the end of it, have as much kinetic energy as what you started with. When two objects bounce apart and they're softer objects like two cars or like a basketball on the floor, then kinetic energy will almost certainly be lost. If you have two objects bouncing off of each other that are hard like billiard balls, then you got a better chance of being elastic. What's that one other thing that we said yesterday? One other way to distinguish between elastic and inelastic. If the two objects stick together, it must be inelastic. If the two objects bounce apart in the collision, it might be elastic, it might be inelastic. So here's the deal. If you get two objects that stick together, we don't even have to do a calculation. We know it's going to be inelastic. If you get two objects that bounce apart, could be elastic, could be inelastic. You got to do a calculation to make sure which one it is. You can make a reasonable, educated guess based on whether the objects are hard or squishy. If they're squishy, it's likely to be inelastic. If they're hard, it's more likely to be elastic. But we still got to do that calculation. Now, what does that calculation look like? Well, you got to calculate EKI, and you got to calculate EKF, and you got to compare them. That's it. If they're the same values, it's elastic. If they're different values, then it's inelastic. All right? Now, we're going to do a problem in just a second here, but a couple more things that I want to mention before we do that problem. Firstly, we're calculating the kinetic energy before and after in the system. So if there's two objects, it would be 1/2 m1 v1i squared plus 1/2 m2 v2i squared, so on. depending upon how many objects you have. Secondly, kinetic energy is a scalar. If we have a direction given to us of the velocity, it's 5 meters to the north, it's 5 meters to the south. It doesn't matter. It's 5 meters per second. 5 meters per second is 5 meters per second, regardless of whether it's north, south, east, west, or 37 degrees south of east. 5 meters per second is 5 meters per second. We never break these down into components. We never worry about an angle. We never worry about a direction because we're talking about kinetic energy, and kinetic energy is a scalar. All right, let's take a look at the problem that we have on page 482. It says a 0.160 kilogram billiard ball traveling at 0.5 meters per second to the north strikes a stationary snooker ball and rebounds at 0.023 to the south. The snooker ball moves off with 0.465 to the north. We want to find out whether it's elastic or not. Honestly, the first thing that I'm thinking when I start reading this question is conservation of momentum, because it's a collision. As I read on and it says determine if it's elastic or not, well, that kind of redirects me to a kinetic energy calculation. In the end, conservation of momentum is valid here. It's a collision. The only thing with conservation of momentum is it's not going to get you anything. You have everything here. You have all the initial and all the final velocities. Okay, you're not going to get anything if you have everything already. So, knowing that it's a kinetic energy calculation, let's write down some givens, and then let's do that calculation. We're going to say M1 is 0.160 kilograms. Okay, that's the billiard ball, and it's initially traveling V1I at 0.500 meters per second. Okay, it strikes a stationary snooker ball. M2 is 0.180 kilograms. And we're going to say V2I is 0 meters per second because it's stationary, it's at rest. The billiard ball hits the snooker ball, and the billiard ball rebounds at 0.0230 to the south. We're going to say V1F is equal to negative 0.0230 meters per second. And we're going to say V2F, the snooker ball final, is equal to positive 0.465 meters per second. We want to find EKI, and we want to find EKF. Kinetic energy initial is equal to 1/2 M1 V1I squared plus 1/2 M2 V2I squared. And the final kinetic energy is almost the same thing. 1/2 M1 V1F squared plus 1/2 M2 V2F squared. Why am I not setting these equal to each other? I did that with momentum, right? PI equals PF. I'm not doing that with kinetic energy. How come, Greg? Yeah, we don't know, right? We know that momentum is equal, but we don't know that kinetic energy is equal. So that's what we got to find. We can't set them equal to each other unless the question says this collision is elastic. Okay, let's plug in some numbers here. M1 is 0.160 kilograms. V1I is 0.5 meters per second. And this one is 0 because V2I is 0. So we do our calculation there, and I think it works out to be exactly 0.0200 joules. We do the second one. The final kinetic energy, 1/2 of M2 V1F is 0.0230 plus 1/2 of M2 . Have I missed anything there? Greg? Oh, is it? Oh, it is. Yeah, should be, the second one should be, first one should be 0.16, right? Yes. That's not what I meant, actually, but thank you. That's correct. Yeah. Speed should be negative here, negative 0.0230. Is that right? How many people said that should be negative? No, it shouldn't. It's a trick question. There's nothing wrong with what I have there. Why should the speed be positive? It's a scalar. Speed is a scalar. Kinetic energy is a scalar. Remember, when we're dealing with kinetic energy, direction is out the window. Not only do we not care about direction, we don't want direction. Okay, I labeled it here as negative 0.0230 meters per second because just in case I had to do a momentum calculation or something down the road. But if I'm doing kinetic energy, we drop any indication of direction, including angles, including negatives, all of that stuff. Okay? You get a crazy complicated two-dimensional collision question. If you're solving for kinetic energy, it's no harder than this because there's no y components, no x components, no negatives, no positives. This is what you see for all of them, 1D or 2D. Okay, let's calculate EKF there. If we calculate that, we end up getting 0.0195 joules. Is kinetic energy conserved? Is it elastic or inelastic? Boy, it's real close, isn't it? It's really close. Is it close enough? No, it isn't. No, it isn't. How do we know where to round to? Like, if we round to one digit, 0.02, the second one would also be 0.02, and we'd say, oh, wait, it's the same number. It's elastic. But we got to round it to three digits there. Hold on. We got to round it to three digits. We say, oh, wait, it's not the same. It's inelastic. How do we know where to round to? The rules of significant figures, right? We'll look back to our data. We got three digits. We got to round it to three digits. If to the right number of significant figures, it's smaller, even if it's slightly smaller, doesn't matter. We're still going to say it's inelastic. It's real close, but it's still inelastic. All right, your homework for the weekend. Listen carefully, guys. Going to be happy about this, believe it or not. Homework for the weekend of these two questions on page 482. I had already assigned page 499, number 1 to 3 and 5 to 11, in addition to your assignment. I'm going to take a couple of those questions away just because I don't want you to be overburdened this weekend, okay? Instead of page 499, number 1 to 3, 5 to 11, I'm just going to say page 499, number 6 to 10. All right? Have all that stuff done for Monday, please. We'll do an activity on Monday, and then on Tuesday, do a little bit of review, have our test on Wednesday. Have a good weekend, everyone.